Hi, everyone. Welcome back to this week's ZX seminar. Today we have Ben. He's going to tell us the hotly anticipated paper, Fault Tolerance by Construction. And the floor is yours.
Thank you very much, Sarah, for hosting, for having me. Yeah, hey everyone. Just a quick side note, I have you guys on the side screen here, so if I keep looking over to the side, that's because I'm trying to look at you guys. Okay. Yeah, thanks everyone for coming and for your interest. I'm going to present some shared work with Bolisa Poor and Alex Kissinger on fault tolerance by construction, which, as I just mentioned, went live today on Archive. So, in this talk, I'm going to be presenting a framework for fault-tolerant circuit synthesis, kind of based on the ZX calculus. And the basic idea of this synthesis framework is that we start off with some idealized description of some circuit that we want to implement fault-tolerantly. So some circuit and how it's supposed to behave under noise. And then using ZX rewrites as kind of refinements, we can bring that into the shape of a circuit, and finally extract some circuit that implements this linear map that we wanted to implement in the first place. And the interesting thing here is that this final circuit will be fault tolerant by construction, because we've made sure that each individual step along the way preserves the fault tolerant properties of our circuit, and thus this rewrite kind of serves as a witness for the correctness of our final circuit. Now, all of this is based around this observation that two circuits, even though they implement the same linear map, might behave very differently under noise, in that a fault over here on the one circuit might be much more detrimental than a fault on the other circuit. And to reason about all of this, our paper is cut into two parts. In the first part, we introduce this notion of fault equivalence, where we formally define what we mean by two circuits not only implementing the same linear map, but actually behaving the same in some sense under noise. And in this part of the paper, we make the case that this is a very useful notion to think about when thinking about fault-tolerant circuits and FTQC. And we'll make that case by recovering a lot of problems and definitions from the literature that people already think about, kind of making the case that this is already implicitly something people do care about, where a lot of problems of fault-tolerant circuit synthesis in the literature basically boil down to, given this description of some idealized linear map under some idealized behavior under noise, find me a fault equivalent circuit that I can actually implement in practice. And once having made that hopefully convincing case that fault equivalence is something that people already do kind of care about, or at least should very much care about, we'll then adapt the ZX calculus to provide a framework through which we can actually manipulate circuits while preserving their behavior under noise. And we'll show the usefulness of this particular framework by looking at some of these circuit synthesis examples of, like, for example, fault-tolerant cat state preparation and fault-tolerant syndrome extraction. And we'll recover existing protocols and verify their correctness, but also give new circuits that use fewer gates and fewer operations to do the same things, kind of providing new state-of-the-art circuits. So with that in mind, we'll just jump right in. If you guys have any questions, feel free to interrupt me. And yeah, well, let's start with part one, like faults on circuits. So our work can very much be seen as being in line with these more recent developments in space-time codes on circuits, Delphos and Bacon and Gottesman and so on, where we consider faults, Pauli faults on circuits in space-time. So we view our circuits as consisting of different time steps, and gates take us from one time step to the next. And a fault is simply a Pauli that acts on the qubits at each time step. So given a circuit, the potential locations where faults can occur are simply the qubits at each time step, and a fault is then simply some Paulis acting on some of these fault locations. So mathematically, we can actually model faults as elements in the Pauli group to the number of locations. Now, with this definition of what we mean by fault, so what we mean by what are all the things that can potentially go wrong, another thing that we have to define is this idea of what do we mean by one thing going wrong? If one thing goes wrong, what's the worst that can happen? And for this, we define this notion of a noise model, where we say a noise model is simply a set of so-called atomic faults, which are the faults that can occur if one thing goes wrong, if one fault event happens. These are the things that can potentially occur. So the set of all potential faults on some circuit under some noise model is the group generated by these atomic faults. And then we say the weight of a fault, so how many things have to go wrong for this particular fault to occur. The weight of a fault is the minimum number of atomic faults in our noise model that are needed to generate some larger fault. And while there are a lot of different noise models we can potentially consider, phenomenological noise, circuit level noise, in this work, we will primarily, or exclusively for circuits, focus on circuit level noise. So we say for circuit level noise, the atomic faults that we are considering are, well, for each wire, we can have qubit flips. So just some Pauli acting on exactly one wire. Then for each gate, so if a fault event occurs and a gate goes wrong, for each multi-qubit gate, a fault can actually create any Pauli flip on any subset of the outputs. So if we have an n-qubit gate going wrong, a single fault can have any combination, any n can flip any of these Paulis. And then finally, the last set of atomic faults that we think about in this particular noise model is for Pauli measurements, so non-destructive measurements. We have measurement flips, which we model by simply placing an anti-commuting Pauli just before and just after that measurement. And then if a multi-qubit Pauli measurement goes wrong, we can actually have measurement flips along with a qubit flip acting on any subset of the outputs. So maybe to give some examples, if we have our circuit from before, a qubit flip might look like something like this or this. If this C0 goes wrong, we can also have two qubit faults, which still count as a single fault event. And then, for example, a measurement flip of this ZZ Pauli measurement can be modeled by placing an X just before and after that measurement. And then if a fault event occurs and this measurement goes wrong, we can also have a measurement flip along with any Pauli fault acting on the outputs. So these are kind of the basic fault events. These are the things that we consider when we say one thing goes wrong. And then if multiple faults occur, we can create larger faults on the circuit. Now, on top of that, sometimes it's very useful for us to kind of idealize our noise models, to say, okay, yes, we know in practice circuit level noise is a very useful notion to think about, but what if we idealize certain locations as being fault-free? What if we say on this particular wire, as a mathematical reasoning tool, we just allow no faults? So we can, for example, idealize exactly certain wires. And what this simply means is that we remove those atomic faults from our noise model. We can also idealize gates and multi-qubit gates, where then we also remove these entangled multi-qubit gates, multi-qubit faults from our noise model. And similarly, we can do the same for Pauli measurements, where we then additionally also remove the measurement flips. So these are really just mathematical tools to reason about on describing potentially what we would like to have. Now, for Pauli measurements, we actually have two levels of idealization that we think about. We have the fault-free Pauli measurement, as we can see here, where we really just assume nothing can go wrong with that particular Pauli measurement. But then also, as a slightly weaker idealization, we'll talk about fault-tolerant Pauli measurements. When we idealize a Pauli measurement as being fault-tolerant, we say we still allow errors on that Pauli measurement. And in particular, the worst that these faults can do, a single fault can at most flip the classical measurement outcome and or create at most one qubit flip on one of its outputs. And this is kind of an idealization that just makes a lot of sense in reasoning about stuff that is already in the literature, and that, for example, Shor-style syndrome extraction kind of satisfies this condition of a single fault event can at most flip the measurement outcome and or create one qubit flip on the data qubits. So this is something, an idealization that is very useful throughout just this entire work and to reason about stuff in the literature. Okay, so we've now defined what we mean by faults as like Pauli's in space-time. We've defined this idea of noise models and idealizations thereof. And then, well, fault-tolerant quantum computing is all about encoding with redundancy in such a way that errors can be detected and corrected. And for this, we kind of do redundant measurements, and that we do measurements where we expect to know the measurement outcome of that particular measurement. So in a noise-free case, we wouldn't even have to do that measurement. That measurement doesn't give us any new information. However, if for some reason this expected measurement outcome is violated, then we know that something went wrong. Then we know that a fault must have occurred, and therefore we've detected the fault. So kind of following Craig Gidney and others, we define this notion of detecting sets as like sets of measurement outcomes whose parity in the noise-free case is predetermined. I think the simplest example for this would be two consecutive measurements of the same type. Well, we just expect the outcome of the two measurements to be the same. So we expect their parity to be even. However, if a fault occurs in these fault locations, an anti-commuting fault, so an X or Y fault, then we will detect that fault. So for example, an X fault in this first wire will flip the second measurement, but not the first one. Therefore, the two measurements will have odd parity, and we know that a fault occurred. However, on the other hand, an X flip before these two measurements will flip both of the measurements, and therefore we will not notice that something went wrong, because both of these measurements will still have the same outcome. The parity will still be even. So we say a fault is detectable if it flips odd many measurements in some detecting set. And all of this can be reasoned about very efficiently, either kind of using the stabilizer formalism or later in the ZX calculus using Pauli webs. All of that we explain a little bit more explicitly in the paper. For the purposes of this talk, the important part is that we have these kind of measurements and where we expect a certain outcome, and if that expectation is violated, we know that something went wrong. And then similar to quantum error correction, where based on that, where we define this notion of distance. In quantum error correction, the distance of a quantum error correction code is like the minimum weight of all non-trivial, undetectable faults. And in a very similar way, we can actually define a notion of distance for quantum circuits, where we say the distance of a quantum circuit is, once again, the minimum weight of all non-trivial, undetectable faults. So this is a very natural generalization of this notion of distance. And similar to how in quantum error correction, distance and correctability is very closely related. Any faults of weight d/2 are correctable. Similarly, we can actually make exactly the same statement for circuits, where we say if a circuit has some distance d, then any fault of weight d-1/2 must be uniquely identifiable. So we can correct faults of weight d-1/2. And kind of with this particular proposition in mind, for the rest of this talk and also in our paper, we will primarily focus on the detectability of faults, knowing that they can, or faults of half the weight can be corrected, but correcting itself is still actually an NP-hard procedure and something that we don't reason about all that much. We primarily care about preserving the distance circuits. Okay, so we now have faults, we have fault events, we can detect our faults. The entire idea of this paper is centered around this observation that two circuits that implement the same linear map might behave differently under noise. So let's, for example, consider this idealized circuit on the left-hand side versus this more implementable circuit on the right-hand side. Both of them implement the cat state so the GHZ state on 4 qubits. But here on the left-hand side, we interpret wait, sorry, I think was there a question in the chat? Yeah, for the purposes of this talk, it's we know that decoding can be done and that you could, for example, build a lookup table. The problem is how do you do it efficiently? And that's the part that we are not concerned with in this talk. So that is actually future work of like, can you preserve efficient decoding under, for example, these fault equivalences and so on. Yeah. So to come back to this counter example of two circuits that implement the same linear map but behave differently under noise, here we have a fault-free preparation of a cat state, just some idealized magic world in which we can do that, versus this circuit that might actually implement the cat state. And we can immediately observe that on the right-hand side, we have a lot more potential fault locations. And in particular, we have certain faults that actually propagate badly, in that a single fault over here kind of propagates out to create two flips of the data. So to have the same effect as this single fault on the right-hand side, on the left-hand side, two false events would have to occur. Or another way to think about this is if we live in a circuit where we have this idealized cat state, and this circuit has distance 2, meaning all faults of weight 1 are detectable, then if we replace this idealized cat state by this particular non-fault tolerant implementation, then all of a sudden there exists a single fault that propagates out to become a fault that looks like two-fault and might therefore not be detectable anymore. Thus, if we replace this idealized thing by this faulty implementation, there might already exist a single fault that is non-trivial, undetectable. Thus, we might have actually reduced the distance of our code and therefore the error correcting capability. So clearly this is undesirable. Clearly there's something wrong here, that we cannot really equate these two circuits in a noisy setting. And to formalize this idea comes kind of this main definition of this talk, and that's the idea of W fault equivalence. So we say two circuits, a circuit C1 under some noise model F1 and a circuit C2 under some noise model F2, are W fault equivalent if for all faults F1 on C1 of weight less than W, we have either the fault is detectable, in which case we don't really care about it, we can kind of take care of it later, or there exists a fault F2 on C2 that has at most the same weight and has the same effect on the circuit. And to make this a symmetric relationship, we similarly require the same for all faults F2 on C2, there to be an equivalent fault on C1. And then we just write that C1 and C2 are W fault equivalent. And if this holds for all W and N, then we say these two circuits are not just W fault equivalent, but we actually say they are fault equivalent. So maybe to come back to the example before of these two circuits, we have a fault over here that is undetectable. And there exists a fault on the left-hand side that has the same effect, right? So the second condition is satisfied. However, the weight of the fault on the left-hand side is larger than the weight of the fault on the right-hand side. So under this definition, these two circuits are not fault equivalent. In particular, this fault observes, like this fault doesn't have a correspondence over here. So fault equivalence can kind of be understood as for any fault over here, undetectable fault over here, there's a corresponding fault over there and vice versa. And with this, we can now actually capture a lot of ideas that are already present in the literature. So for example, fault-tolerant cat state preparation is usually defined as, if I want to prepare the cat state up to some weight W, that a circuit fault-tolerantly prepares the cat state up to some weight W if all faults of weight less than W are either detectable or create at most as many data flips. Now, this is formally equivalent to saying a circuit C fault-tolerantly prepares the cat state up to some weight W if C is W fault equivalent to this idealized fault-free cut state, followed by some potentially qubit flips on the wires. Because what this condition requires is that for any fault on C of weight n less than W, it's either detectable or it has a corresponding fault over here. And the only allowed corresponding faults on the right-hand side are exactly the data flips. So what this definition is requiring is that any fault on C must either be detectable or create as many data flips on the cut state. So this is exactly the definition that you'd usually find in the literature. And very similarly, we can, for example, say fault-tolerant logical state preparation is find a circuit that is W fault equivalent to perfectly fault-free preparing the logical state on the logicals, and then fault-free doing the encoder. So find a circuit that is W fault equivalent to this idealized setting. Going through another example, fault-tolerant syndrome extraction. So this is something you have to do if you want to do error correction, right? You have to measure all your stabilizers and get your syndrome to then do your decoding and correcting. So fault-tolerant syndrome extraction is the idea is if I have a generating set of my stabilizers S1 through Sm, then a circuit fault-tolerantly implements the syndrome extraction if it is W or D fault equivalent to kind of perfectly fault-free implementing my measurements with nothing going wrong in between. So this is kind of the idealized scenario that we want to achieve for our circuit to be considered fault-tolerantly implementing a syndrome extraction procedure. And oftentimes this is, for example, done by kind of composing fault-tolerant syndrome measurements, where we can now say a syndrome measurement, a circuit C fault-tolerant implements a syndrome measurement if it is fault equivalent to this fault-tolerant syndrome measurement, where if you remember the idealization here where we don't draw this top part in purple, is we've idealized this measurement as fault-tolerant, meaning that fault events can still flip our classical measurement outcome, but a single fault event can create at most a single qubit flip on our output qubits. So a lot of things in the literature of like fault-tolerant circuit synthesis can very naturally be expressed as, given this idealized description of what I would like to have, find me something that is fault equivalent to that I can actually implement on my hardware. We can actually go a step beyond that. We can actually also formalize quantum error correction and fault-tolerant quantum computing in terms of fault equivalence. So usually, quantum error correction, the quantum error correction code is defined via its encoder, which is a linear map for which there exists a decoder such that all faults of weight less than D are detectable by the decoder. Now, in terms of fault equivalence, we can say, look, a quantum error correction code is a linear map for which there exists a decoder such that these two diagrams are fault equivalent. Because what this fault equivalence requires is that any fault here on the left-hand side of weight less than D, it must either be detectable or it must have a corresponding fault on the right-hand side. Since we've idealized the right-hand side as being fault-free completely, the only fault allowed on the right-hand side is the trivial fault. Thus, what we are saying is that any fault on the left-hand side must either be detectable or trivial. And this is exactly the notion that we had earlier when defining fault-tolerant error correction. Now, if quantum error correction is all about encoding data with redundancy in such a way that errors can be detected and corrected, then we can now give a circuit-centric definition of fault-tolerant quantum computing using fault equivalence, where we say, okay, fault-tolerant quantum computing is all about encoding computation, so i.e. circuits, with redundancy in such a way that errors can be detected and corrected. So given some idealized computation C that you want to do, you want to break into someone's email account, we say a fault-tolerant encoding of that circuit is a circuit CFT that is default equivalent to the idealized fault-free computation that you want to do in the first place. Because once again, this fault equivalence requires that any fault on the left-hand side of weight less than D must either be detectable or trivial. So we've now define, oh yeah, oh sorry, yes, there are some properties of fault equivalence. So we've now defined fault equivalence as this notion of like thinking about the behavior of circuits under noise, and we're trying to make the case that this is very useful to think about. Now, what are the properties of fault equivalence? Well, one of the first things you might notice is this idea that for any fault combination of up to some weight on the left-hand side, we have to check all fault combinations up to some weight on the right-hand side. That's a lot of checking that you have to do. And more formally, we can say, well, checking whether two circuits are fault equivalent is at least NP hard. Formally, we can reduce this kind of to calculating the distance of a stabilizer code, which is known to be NP hard. So we can say that even just checking whether two circuits are fault equivalent is very difficult. So if we want to do fault-tolerant circuit synthesis, we just have to be very careful, because even just the final check, if we have to compute it brute force from scratch, can be very expensive. However, there are some properties of fault equivalence that are actually very useful, and they will be very useful throughout the rest of this talk. The first one is that fault equivalence is compositional. So if some circuit C1 is fault equivalent to C1 prime, and C2 is fault equivalent to C2 prime, then the sequential composition of C1 and C2 is fault equivalent to the sequential composition of C1 prime, C2 prime. And similarly for their parallel composition. So if for some reason you have two large circuits and you can break them into smaller components for which you can individually check that these components are fault equivalent, then you've also shown that the overall circuit is fault equivalent. And another property that we'll be making use of is the transitivity of fault equivalence. That if C1 is fault equivalent to C2 and C2 is fault equivalent to C3, then C1 is fault equivalent to C3. Okay, so we've defined fault equivalence. We said a lot of problems that we care about and that people care about and that we can be expressed in terms of that. So how do we now do fault-tolerant circuit synthesis? How do we solve this problem of fault-tolerant cat state preparation? Now, this actually brings us to the second part of the talk, the ZX calculus, the reason we're all here. Well, the ZX calculus is a language that is particularly suitable for manipulating circuits. And we will, throughout this talk, kind of adapt the ZX calculus to not only preserve semantic equivalence, or the underlying linear map, but also fault equivalence. So I'll give a very quick introduction to the ZX calculus in case there are some people here that are more on the QEC side and have not been exposed to the ZX calculus quite as much. The ZX calculus is a graphical language to reason about quantum circuits. It consists of these two generators, the green Z spider and the red X spider, which we can compose sequentially and in parallel. And it turns out that just by composing these two spiders in that manner, we can actually represent any linear map from n qubits to m qubits. This is the Clifford fragment of the ZX calculus. So this only works for stabilizer circuits, but there is also a universal set of spiders. And this means that we can, for example, represent a lot of gates that we care about. We can have state preparation, single qubit gates, multi-qubit gates, and measurements. But the real power of the ZX calculus comes from the fact that you can actually also manipulate these diagrams using diagrammatic rewrites. One of the main rules that is oftentimes implicit is this idea of only connectivity matters. You can move your spiders, as we call them, you can move them around as long as the connectivity stays the same. The underlying linear map that these diagrams represent is being preserved. And then on top of that, there is these eight rewrite rules that are shown to be complete for the Clifford fragment in this case, meaning that any two ZX diagrams that represent the same linear map can be shown to be equivalent just using these rules. And where this, amongst other things, comes in handy is for circuit synthesis using the ZX calculus. So if I, for example, want to synthesize a circuit that prepares the cat state, what I can do is I can translate it into a ZX diagram, kind of basically just using this lookup table here. I can translate it into a ZX diagram, and then I can use my ZX rewrites to deform that diagram until I get something that actually looks like a quantum circuit again, where we have a bunch of state preparations here in the beginning, And then we can see that there is just these C-naughts over here. So from this diagram, we can very naturally extract the corresponding quantum circuit. Now, if we actually look at this circuit just for a second, we'll observe that this is the counterexample that I gave earlier of how not to prepare the cat state in a noisy setting. And that's because the ZX calculus preserves semantic equivalence, right? It preserves the underlying linear map. It does not, as at least the vanilla ZX calculus, preserve fault equivalence, which is what we're going to talk about next. So for that, we first have to define noise on ZX diagrams. Previously, we had Pauli's in spacetime. Similarly, here we will have just Pauli's, and in our case, the fault locations are the edges of the ZX diagram, and a fault on this diagram is a Pauli in the Pauli group to the number of edges that acts on some of these edges. And then we have to say, okay, what do we mean by one thing going wrong? And for quantum circuits, we have this circuit level noise, which cared quite a lot about where are my gates. Here we'll define a slightly simpler model, because one of the key features of the ZX calculus, this is going back, is this exact OCM rewrite. The fact that we can move things around. And to me, kind of intuitively, this corresponds to the idea of like, you can interpret time differently. You can kind of, where my qubits flow, which edges are part of like a wire on which a qubit lives and which edges are internal to a gate. You can move that around. So this is a key part of the ZX calculus, at least in my mind, and this is something we want to preserve. So we define a noise model on ZX diagrams that we call edge flip noise, where we say the atomic fault events are simply Pauli's that affect exactly one edge flip, one edge. So this would be a fault of weight 4 because 4 edges are affected. Now, we do eventually want to reason about circuit level noise, so we'll have to take care of that in some other step, and we will take care of that, but that is something we'll take care of in a second. And then similar to how we idealize our circuit level noise model, we can also idealize the edge flip noise model, where we say, okay, we just idealize certain edges on our ZX diagram to be, by definition, fault-free.
Excuse me, I have a question.
Yeah.
So when you say you idealize an edge, what does it correspond to physically when you're implementing a circuit?
It doesn't. So if you actually want to implement the circuit, you shouldn't have any idealized edges or gates anymore, because you cannot tell your quantum computer to not make a mistake here. It's more, I view it as a mathematical reasoning tool for like intermediate steps. It's to define what I want in the beginning. And then if I actually want to have something implementable, I will have to get rid of these idealized edges.
And do you get rid of all of these idealized edges one by one? Or is there a systematic way to get rid of them?
We don't necessarily have a systematic way at the moment, but I'll show us some examples of how we get rid of them later.
Thank you.
Okay, so we now have our noise model on ZX diagrams. The question was, how do we fault-tolerantly prepare a certain gate that we want to implement? The way we did it earlier with the vanilla ZX calculus was we kind of took the description of what we want to have, translated into a ZX diagram, manipulate that ZX diagram until we had something that looked like a quantum circuit, and then we extracted our circuit from there. And we'll have a very similar procedure. But now we have to make sure that we always preserve fault equivalence along the way. So we take a quantum circuit that describes the idealized thing that we want to have and translate it into a fault equivalent ZX diagram. And this is the step where we have to take care of these different noise models, because we have a quantum circuit under some noise model, such as circuit level noise, and then we have our ZX diagram under edge flip noise. Then we manipulate that diagram while preserving fault equivalence. And finally, we will once more extract a circuit from the diagram fault equivalently. So there's kind of two things we have to take care of. We have this translation between quantum circuits and ZX diagrams, where we have to preserve fault equivalence. And then we have the manipulation of our ZX diagram, where once again, we want to preserve fault equivalence. So let's start with the first part. Let's start with this, the equivalence between ZX diagrams and quantum circuits. We say a ZX diagram is a fault equivalent representation of some quantum circuit. if the two are, well, fault equivalent. I feel like I'm saying the word fault equivalent a lot, but like that's the central concept here that everything revolves around, right? Um, and this can generally be quite hard because we have, well, arbitrary noise models, especially with, like, for example, circuit level noise. We have the potentially entangled faults. And then on the other hand, on ZX diagrams, we only have individual edge flips as our atomic faults. And there is a general procedure for any quantum circuit under any noise model to build from that a fault equivalent ZX diagram, where we kind of use these fault gadgets that we introduce. But especially for like circuit synthesis purposes, these can sometimes be tedious to reason about. They're very useful in some contexts, but like for the circuit, for the synthesis process, sometimes they can be rather tedious to work with. So what we also did is we tried to identify certain circuits under certain idealizations that are more naturally fault equivalent to a ZX diagram where we don't have to use fault gadgets. So, for example, an observation that we can make is any gate that we idealize as fault-free is has a very natural fault equivalent ZX diagram. What we can observe is that a fault-free gate, the idea here was that it can actually, a non-fault-free gate can create entangled faults on subsets of its output. But we remove that. If we idealize the gate as fault-free, the only faults that can occur are qubit flips on the individual wires. And these very naturally correspond to just edge flips on the boundary wires of the ZX diagram. So if we translate some gate into a ZX diagram and idealize all the internal edges as fault-free, then the two things will be fault equivalent. So for example, for the cat state, we can translate it into a ZX diagram. Well, we'll observe that there are no internal edges, so nothing to idealize here. But any qubit flip over here very naturally just corresponds to an edge flip over here and vice versa. So clearly those two things are fault equivalent. Similarly, for a fault-free Pauli measurement, if we just idealize all the internal edges, then any qubit flip on the inputs or outputs just corresponds to edge flips on the inputs or outputs, but no other faults are allowed on either of them. Now, on top of that, we idealized, so for the multi-qubit Pauli measurements, we had this idealization, this very strong idealization as being fault-free. And then this slightly weaker idealization of being fault tolerant, where we said, okay, the atomic faults can at most create a qubit flip, a measurement flip, as a flip of your classical measurement outcome, and at most one flip of your data qubits. And for this idealization, we can actually observe that it's fault equivalent to this particular ZX diagram, where we do not idealize the internal edges as fault-free. And the way we can check that is simply by going through all faults on either side and checking that they have an equivalence on the other side. So for example, for the measurement flip, which we modeled as like an anti-commuting Pauli before and after, this in a ZX diagram can be written down like this, but that's actually equivalent to a single edge flip over here. And then similarly for a measurement flip along with like a data flip, we can once again find a single edge flip, in this case a Y edge flip, that has the corresponding effect. And in a very similar manner, we can go through all possible atomic faults on the left-hand side and find an equivalent on the right-hand side and vice versa. Now, for non-idealized gates, multi-qubit gates, it gets a little bit more tricky. For example, for the CNOT, we can actually create any, like a CNOT fault event can create any kind of Pauli fault on the output qubit. So there's 15 non-trivial faults that can potentially happen. And we've found no way to model that without fault gadgets. However, there are certain composed settings, composed circuits, where this more natural fault equivalence actually does occur again. For example, a CNOT followed by a measurement, because the stabilizers of that measurement will take care of the non-trivial faults. So once again, we can just simply go through all possible faults over here and see that there is a corresponding edge flip over here and vice versa. And another one that we can identify is if you prepare a state and then do a CNOT. This again has a very natural fault equivalence in ZX diagrams. And these two circuits will be quite useful throughout the rest of this talk for extracting our quantum circuits. Now, the other part that we have to do in our synthesis procedure is rewriting our diagrams. We have to manipulate them. And once again, we can say, okay, now a rewrite is fault equivalent. Well, if it preserves fault equivalence, right? We can see a rewrite is taking some diagram D1 into a diagram to a diagram D2, and we say the rewrite is fault equivalent if those two diagrams are fault equivalent. And there's a bunch of these rewrites that we've found. A lot of these also already come from our previous paper where we called them distance preserving rewrites. And the way you prove this equivalence is, once again, you just check any possible fault over here and check that there is a corresponding fault over there. And we can go through quite a few of these. I think the general idea is kind of clear now. An interesting part here is that some of these rewrites actually introduce new detecting sets, right? Fault equivalence is not just that any fault over here has a correspondence over here, it's any undetectable fault over here has a correspondence over here. So some of these rewrites actually introduce new detecting sets. Therefore, kind of we only have to check the undetectable faults and not all possible faults. And this is an NP-hard problem, but all of these rewrites are relatively small or sufficiently structured for us to really rigorously prove this equivalence. We can actually also use our tools to go to larger families of circuits where we can once again kind of show that all undetectable faults over here have a correspondence over here. Now, all the rewrites I've shown so far were fault equivalent rewrites, and in that any fault, no matter what weight over here, has a correspondence over here. But we can also identify some W fault equivalent rewrites, which will potentially lead to circuits that use fewer gates, and therefore might just be simpler, cheaper to implement in some settings. Okay, so we've defined this notion of fault equivalence. We've said this is very useful for fault-tolerant circuit synthesis. And now through the ZX calculus and through this adaptation of the ZX calculus, we've found a way to kind of manipulate diagrams while preserving fault equivalence. Let's actually apply it to some of the problems we stated earlier. Fault-tolerant cut state preparation was find a circuit C that is fault equivalent to this thing. Starting with the cut state on 4 qubits. What we can do is we can take the cut state, we translate it into a fault equivalent ZX diagram. Remember earlier we said that any fault-free gate has a very natural correspondence in ZX, and this was one of the examples we saw. And then we can use our fault equivalent rewrites to manipulate that diagram. These are the rewrites that I just showed you. I'm using a little bit of OCM here, so only connectivity matters. We're moving the spirals around until eventually we get a ZX diagram that once again looks like a quantum circuit, where we prepare some qubits, we have some CNOTs, and we do a measurement. And now if we actually look at this very closely, we can identify these fault equivalent components that we saw earlier. Because if we can build this diagram out of fault equivalent components, then we know it will be fault equivalent to the corresponding quantum circuit. So here we have these preparations along with CNOTs. And then we have the CNOT with a measurement. And finally, single qubit preparations are also fault equivalent. Thus, we know that all of these individual components are fault equivalent. By the theorem that we proved earlier, their composition must also be fault equivalent. Therefore, we know that this circuit is fault equivalent to that diagram. We can kind of read the circuit as preparing an ancilla qubit, a flag, entangling it with the data, doing the non-fault tolerant procedure that we had earlier, once again entangling the flag and measuring it out. Now, the way these flag circuits are usually built is by you start with a non-fault tolerant circuit, you check which are the faults that propagate badly, and then you construct flags to catch those. Our construction is different. We are fault tolerant by construction because we know that any fault over here has a corresponding, is either detectable or has a corresponding fault over here, is either detectable or has a corresponding fault over here, and therefore any fault over here, no matter the weight even, must either be detectable or have a corresponding fault on our idealized circuit. So must either be detectable or create at most as many data flips. And in contrast to these brute force approaches where you have to go through all possible fault combinations, which gets very difficult as your circuits get larger and have more faults, we can actually use this to kind of synthesize circuits, like arbitrarily large circuits, if we find some nice rewrite strategy, right? So for an arbitrary legged cat state, we once again can apply exactly the same procedure where we translate it into a fault equivalent ZX diagram, use our fault equivalent rewrites until we get something where we can identify the fault equivalent circuit components. And therefore, we will have found a fault equivalent quantum circuit that is fault equivalent to our idealized description. So we can build a 2n-legged cat state out of 2n-legged cat state using these measurements. And this works for arbitrary weight cat states. Now, there are some nuances here about like you have to actually correct based on the measurement outcome. We treat this more rigorously formally in the paper. For the purposes of this talk, I'll just glance over these corrections. Now, preparing a cat state at arbitrary, and this is at arbitrary distance, right? For any fault, no matter the weight, we know that these two things are fault equivalent. Now, in practice, we often work in circuits that have a certain distance, right? We don't need to protect against faults of distance 100 because if our circuit only has distance 3, at that point, if we ever get to distance 100, we have a problem anyways. So we can also actually synthesize cheaper circuits by not using fault equivalent rewrites, but using W fault equivalent rewrites, where we can exactly use the same strategy, but here we don't use the fault equivalent rewrite, but the W fault equivalent rewrite. So this only holds up to some weight. And then we can synthesize a cheaper protocol that only uses W many measurements and 2W many CNOTs instead of N many measurements and 2N many CNOTs. So at large N, this might actually reduce the gate count significantly. Another example where we have applied this framework is for fault-tolerant syndrome extraction. So once again, the problem was that if I have some sort of stabilizer code with a generating set of my stabilizers as 1 through as m, I want to find a circuit that is fault equivalent to implementing these measurements fault-free with nothing going wrong in between. Now, this is a difficult problem, but this is a problem people have previously thought about, right? So one solution to this is given by Shaw. And we can use our framework to kind of verify the correctness of Shaw-Star syndrome extraction. So Shaw breaks the problem into 2 steps. First, he observes that these fault-free idealizations, they're quite strong, right? But if I repeat my measurement schedule fault-tolerantly d many times, that is actually fault equivalent to this fault-free implementation. And you can check this because it only holds up to some weight d, so you know that there must be one iteration that is fault-free, and you can formally reason that these two things are fault equivalent. So the problem that is remaining is how do I implement the fault-tolerant individual syndrome measurements? And so how do I do fault-tolerant syndrome measurements? Now, Shaw observes that any syndrome measurement up to some local Cliffords is equivalent to just the all Z syndrome measurement. So he focuses on the all Z syndrome measurement, where the question is, how do I implement this fault-tolerant measurement? Well, once again, using our procedure, we can verify the correctness of Shaw-Star syndrome extraction because we can say, well, we translate it into a ZX diagram. We rewrite that ZX diagram until we get the circuit where we once again observe our fault equivalent components. So we can say fault-tolerant Shaw-Star syndrome extraction is correct. So this circuit where we fault-tolerantly prepare the cat state, for example, using the procedure above, then we transversely do the CNOTs, and then we transversely have these destructive measurements. That's Shaw-Star syndrome extraction, and we've now proven its correctness with our framework. Now, the way people usually prove correctness of Shaw-Star syndrome extraction is by appealing to the transversal nature of this construction. But for us, we don't need to do that. We can actually, we have a slightly different proof strategy, which allows us to verify correctness of non-transversal circuits as well. But first, I think Rosine has a question.
What is the relation between, so on the left-hand side, there's k pi, and then you have k1 through k4 pi. Like, how is that equal? And like,
Yeah.
because on the rightmost diagram, it's a measurement. It's something you can't control.
Yeah. So yeah, there are some details here that I'm glossing over. So you have to be clear, and this is also related to the corrections that I was talking about earlier. In this particular case, the parity of these measurement outcomes will give you this outcome. Yeah, you have to be careful when rewriting these things because we don't work in a post-selected setting. We work in a setting where we don't have control over these measurement outcomes. But what you can see is that no matter what the outcome here is here, that kind of corresponds to some k over there. So you have to keep track of these parameters and how they are updated, something that indeed I am glossing over in this talk.
Sorry, I actually have a similar question. So in your
Yeah,
previous paper, you were saying that the fault tolerance is defined under the notion of post-selection. So you kind of
yeah,
know what is the anticipated outcome, and then you can
yeah,
decide whether there's an error in the circuit. Now, if you
yeah,
don't do this post-selection, what would be the like because you repeat the measurement d times,
yeah.
and what is actually happening when you collect the measurement outcome from every measurements? Do you have a measurement table? Do you compare them? Do you get
Yeah, so okay. So in our previous paper, we kind of assumed these measurement outcomes to all be zero. So we do still assume that we have these parities of we still have detecting sets, right? We still have this notion of talking about detectability of faults. However, we don't assume all measurement outcomes to be zero. Because you can't if you go beyond like the QEC setting to like also logicals and stuff, you can't necessarily always assume the measurements to be zero. However, we still have, in terms of Pauli webs and stuff, the notion of talking about detectability of faults, because a fault is detectable if it, well, flips odd many measurements in a detecting set, or equivalently, if it anti-commutes with a detecting region. So there are still ways of talking about this, but you have to be careful. There's more nuance that comes in, or well, a different kind of nuance, I guess, that comes in contrast to this post-selection on zero.
is this still efficient to do this? Like if
Yes,
you
yes. Yeah,
okay.
you can still do Pauli webs can be calculated efficiently and all of that can still be reasoned about yes, efficiently.
Okay, thanks.
Um, okay, so we've verified Shor-style syndrome extraction. Indeed, you have to be a little bit careful about the measurement outcomes, and there's even more care you have to do in the future circuits that we're proposing, but I will glance over that. But now we've verified correctness without having to appeal to the transversal nature. So we can now come up with non-transversal constructions. We don't have to stop at verifying, we can start optimizing, right? So if we have the problem of how do I fault tolerantly implement the syndrome measurement, I can once again do the same stuff as Shor, but then I can go a step further. I can just take these two measurements and using OCM, only connectivity matters, I can bend them around. Now I get a new circuit where once again I can identify my fault equivalent components, and thus I get a new circuit that uses half as many qubits. Instead of using 4 qubits and 4 measurements, I only use 2 qubits and 2 measurements. But now, instead of having to prepare the cat state fault tolerantly, we have to implement this cat-like linear map fault tolerantly. But using our rewrites, once again, we can actually come up with circuits that do that in practice. So we found a way to fault tolerantly implement something that is fault equivalent to Shor-style syndrome extraction, but uses fewer auxiliary qubits. And we don't have to stop there. We can actually come up with wild protocols that, again, are fault equivalent to the syndrome measurement. But for example, in this case, we have this teleportation-like thing over here, where in the beginning, our data qubits are on the first 4 qubits, and then by the end, our data is on the last 4 qubits. And this kind of allows us to move the qubit around the chip, which might help you kind of account for certain connectivity issues on superconducting chips or for leakage reduction and stuff. So there's a lot of interesting things that this more dynamic perspective allows you to then do. Okay, I'll very quickly, because we're running out of time, and that's fine anyways, I'll very quickly run through another example. So another way of solving syndrome extraction is offered by Steen, which only works for CSS codes. But once again, we can use our framework to verify the correctness of Steen-style syndrome extraction. We translate it into a fault equivalent diagram. We fault equivalently manipulate that diagram until eventually we get the circuits proposed by Steen. So we can prove the correctness of Steen-style syndrome extraction using this framework. And then from there, we can also start optimizing Steen-style syndrome extraction, where once again, we just take half the auxiliary qubits and bend them around, where now instead of having to prepare the logical state fault tolerantly, we have to do this logical state like linear map. And while we don't give a general procedure for this in our paper, for the cat-like linear map, we gave a general procedure. For this one, we don't. But we give one example, in particular, the Steen code. So we ask the question, can we do this optimization for the Steen code in particular? So optimizing Steen-style syndrome extraction for the Steen code. Now, implementing this zero-like, this logical state-like linear map is quite difficult, similar to how fault-tolerant state preparation is actually quite difficult. But because our framework very naturally captures the things that people have been thinking about in the literature, we can also actually kind of just steal their stuff or borrow or use, where a solution to this problem has been given in 2016, like a fault equivalently preparing this logical state for the Steen code. So this solution has been thought up by someone else very efficiently, and we can now use that, plug that into our Steen-style syndrome extraction, and do the optimization procedure outlined earlier to get a new circuit that fault-tolerantly implements Steen-style syndrome extraction, but once again uses fewer qubits, fewer measurements, and fewer CNOTs. And that brings me to the end of this talk. Kind of to recap, we've defined this notion of fault equivalence. We've kind of made the case that this is already intrinsically present in a lot of the thinking around fault-tolerant circuit synthesis, and it would be nice to make it much more explicit. And once we've made that case, we actually provided a framework based on the ZX calculus to manipulate circuits while preserving fault equivalence. Now, a lot of our work, and especially these examples in the last part, all of them were done by hand. So this is us kind of really looking at it real hard and doing these ZX rewrites by hand. I think a very interesting question is, can we automate some of these procedures? Can we optimize? Find algorithms that do fault-tolerant synthesis and optimization based on these rewrites? Now, another assumption that we've made throughout all of this is this: we've been talking about adversarial noise, and that we've been talking about the worst case behavior of circuits under noise. If at most so many faults occur over here, what's the worst that can happen over there? And this is also, for example, reflected in the fact that we don't assign any probabilities to our faults. We simply say, look, these are the atomic faults. Now, a very interesting question would be, how do you go from this worst case analysis under adversarial noise to an average case analysis under stochastic noise? So what's the average case behavior of our circuit? And can we reason about average case fault equivalences? Another question for future work is this decoding problem, right? If I start with a circuit that has an efficient decoder, can I preserve decodability, efficient decodability under my rewrites? Because I am changing the number of detecting regions, I am changing the decoding problem. And then maybe one more piece of future work to mention is all of this has been done for Clifford circuits, and like most of the space-time formalisms I'm aware of are for Clifford circuits, which is a fragment that is incredibly useful for error correction, and there are a lot of problems to be solved here. But in the long term, it would be really quite interesting to obviously go beyond Clifford to something that's not classically simulable. However, that seems like quite a task. Yeah. So I want to thank you all for your attention. I'll just flash our archive ID once more, and I'm happy to kind of answer any questions.
Thank you, Ben, for the very interesting talk. So we can give him emojis or like just clap. If you have questions, feel free to raise your hands, and you can just go ahead and ask.
Hello. Hi, Ben. Very good talk. Thank you for that. Um, just so I'm clear, so the definition for fault equivalence, does that mean the faults have to be on the same qubit? So if you
Um,
had two circuits that had like the same degree of faults,
yeah.
they were on different qubits, would those be fault equivalent?
If the so the what we say is kind of if you place a fault on a qubit,
Hmm.
you get a new circuit, right? You can kind of view that as, oh, I take my circuit and I just place a particular gate on there that does the corresponding Pauli rotation, right?
Hmm.
So we say two faults are equivalent if their effect on the circuit is the same. So if
But they
kind
could be in different. The effect could enact on different qubit outputs, though, right?
if it acts on different qubits, that's totally fine as long as you make
Right.
sure that the effect is the same. Yeah. So one way to achieve this is like if you do something stabilizer equivalent, you could actually act on all the other qubits as long as the effect is still the same. So there indeed is scenarios where you can find faults that act on different qubits but have the same effect. What we care about is the weight and the effect. Yeah.
When you say effect, do you mean that if there is a fault, the bit output that you measure that itself could also be on a different qubit, right?
So what I mean is kind of in ZX language, one way to put it is you get a new ZX diagram if you
Hmm.
place the fault on the diagram, and that has a different linear map. That linear map should be the same between the different faults.
Okay. Thank you.
So I have a question. I'll let other people. Oh, actually, sorry, Sakale raised their hand. Please go ahead.
Hello, I have a question that do we know the limitations of those fault-tolerant writing rules? Like, are they complete,
Mm.
or is there anything that we cannot do?
Yeah, they're not complete. Definitely, likely not complete. We're currently thinking about like automated ways of proving fault equivalence using some set of rewrites. So part of the problem is that these rewrites are local, and I'm fairly sure that fault equivalence is not local. In that, whether a certain rewrite is fault equivalent in a very local context might depend on the stabilizers of the surrounding circuit. So if the input state that you chuck into your linear map has certain stabilizers, then a particular rewrite might be fault equivalent or not. But calculating the stabilizers of the inputs, that can be very much dependent on something that happened very early on in your circuit. So this can be very far away from where you want to do the rewrite. So I think as is, if we only consider local context, it's not going to be possible to give a complete set of rewrites. Again, because of this idea of like, okay, but maybe this particular fault that propagates out badly is trivial in this particular context, because in this particular context, it corresponds to a stabilizer. But calculating kind of the stabilizers of the surrounding context is a global task. It's efficiently computable, but it's still non-local. Therefore, these local rewrites as we have at the moment, I don't think can be complete.
And on the other hand, usually to prove completeness, we need a normal form. What do you think would be a normal form for your distance preserving circuit?
Yeah, so this is something I've been working on with Max, who I think is also here somewhere, where we kind of use these fault gadgets as ways of not just representing potential entangled faults. I don't know where they are. Yeah, not just a way to represent entangled faults, but also as a way to where you can actually manipulate these fault gadgets very efficiently. And as with that, you can actually reason about the effect of faults on circuits using relatively local rewrites. And then you can kind of potentially think about a normal form where you have a fault-free Clifford circuit and then just a bunch of fault gadgets on all the outputs. And then the question is, okay, is the Clifford circuit, this fault-free thing, fault equivalent? Well, that we can use our usual normal forms. And then are these fault gadgets that we get at the end, which might be very highly entangled and interacting on all the output qubits or boundary qubits, are they fault equivalent? And I think the latter is A, well, it's NP hard, as we've shown to prove, but B, also inherently non-local.
Thank you. And also for recording purposes, Miriam just mentioned a remark. Let me just read it out. They said we don't strictly need a normal form for completeness, though of course it does usually make the things easier. Thank you, Miriam.
Yeah.
Well, this actually made me realize because now we have a full house of researchers from all fields of quantum computing and ZX calculus. Maybe this is a good opportunity for Ben to ask people here questions. And then maybe because everyone has tight schedule, maybe Ben, if you have questions, you can first ask. And then for the audience, if we have questions, we can ask Ben after Ben asks the audience. What do you think? Does that work?
Yeah, that works for me.
Okay.
Yeah, I think one of the questions that has been bugging me quite a bit is this question of like, I'm not sure if people here have been thinking about detecting regions. Like detecting regions is these detecting sets, and they can be local or they can span the entire circuit and everything. And I'm wondering whether people have been thinking about like, okay, maybe this is a way to phrase it. There is a difference between the distance of a code and whether a fault is detectable. So we can have a fault that is very high weight, but if it's far enough, if we have a fault of weight d minus 1 over here and a fault that is d minus of weight d minus 1 over there, this fault, even though it's of far beyond the distance of our circuit, might still be detectable. And I feel like in the circuit-centric literature, I don't know if people have been thinking about this a lot. In the circuit-centric literature, there are ways of thinking about this, but I'm wondering whether anyone has kind of thought about like faults on circuits and the relationship between distance and detectability of like larger weight faults. This might also be very specific because it's kind of this particular perspective on fault-tolerant quantum computing. I'm just wondering whether people have been thinking about the relationship also. This goes in the direction of the relationship between adversarial and stochastic noise. I'm not sure if this is a well-formed question. This is more a thing that has been bugging me. Maybe a more reasonable question is, have people been thinking about circuits under noise? And what are kind of the ways you've been thinking about this? I think one way is via the detecting regions that like Gidney and cohorts are doing. I'm wondering whether there are other ways of thinking about the behavior of circuits under noise that you might be aware of.
Hello, this is Leah. I do have a comment
Yeah.
about in response to your uh not question but also thinking things to think about. I guess one is one is that something that's really been really bothering me uh is that it's difficult to have a description of non-qubit noise in the sense that you by the time it's already a qubit polyerror, it's already been converted from some other phenomenological noise model that's like not that and then this conversion has this really high um could have this really high cost to doing this conversion. So something that's been really bothering me. If this is like some kind of like quantum error correction like therapy session with anonymous or something. Just kidding. But it's like if you have some noise, for example, like say leakage to outside the qubit system, or if you have like other other kinds of noise that aren't describable in the qubit setting, then it's not clear to me how you could represent that
Yeah.
with just qubit ZX maps, and that's something that really confuses me.
Yeah, that's not something I've been thinking about too much. There's indeed, I mean, there are always these simplifying assumptions that people are doing, and I think Pauli noise is kind of a very common one. I'm not fully sure what I think it really like for certain types of noise, this is definitely insufficient. would be an interesting question of whether you can actually talk about these other kind of noises in a similar fashion. Yeah.
I mean, maybe to jump in on that, I mean, the reason that Paulis are interesting is because they form a basis for all matrices, right? So by looking at linear combinations of things, we can actually get very far. I guess in general, obviously, like some maps will take you out of the space of pure states, so then you'd need to think about mixed states in general. But even then, I think it should, in principle, still be fine to, like, Pauli's should still span everything that happens. Potentially, I guess Pauli's in a larger space. Like we might potentially want to introduce an environment and stuff that happens there. Again, this is not at all my area of expertise. This is just kind of thinking about Pauli's in general, and because I was just teaching introduction to like the very basics of quantum error correction last week.
Yeah, no, I mean, yeah, exactly. You get quite far, but I think for certain kinds of noise, it's still, I mean, something that we clearly don't think about here is like loss and stuff, photon loss or something that's completely different issue that people think about.
Yeah,
I
that's
feel like,
yeah, I mean obviously like correlated things is also again different.
yeah,
Loss is just like completely tracing out a qubit, right? So if you're
yeah,
I think if you're working in a mixed state setting, then you can model loss in like using Pauline noise, I would expect, because you just kind of, yeah, completely trace out one thing. And then I think that should still be like a linear map that you can model. But yeah, this is just me sort of speculating off, yeah, the bits that I know that I have not actually looked at this in very much detail.
yeah. And I think it would be, yeah, it would be something you can model. It would, yeah, it would require some additional attention, I guess, or separate attention. Yeah.
Yeah, you could think of like loss, I guess, as discarding a qubit in an ambiguity graph. Like you don't have the access to one measurement outcome. So
Yeah.
so it's like it's not the first effect would be to remove the node and the edges that it's connected to, right?
Yeah.
And then it could induce some Pauli errors on the remaining qubits. I think, I don't know.
Yeah.
Seems a bit.
Yeah, I mean, I think loss isn't quite like I mean, in MBQC to remove a qubit, we Z measure it, right? Whereas loss is a tracing out, I think, not a Z measurement. So that is a bit different.
Yeah, it's like there's two, uh, but if it's like there's two branches, but both of them are like discarding the qubit, like removing the node.
Yeah. I guess it's sort of like yeah, like linear combination of like you've measured it, but then you've forgotten the results. So that's kind of yeah, one way of I think tracing out.
When you
It's non-trivial.
sorry, Giovanni, earlier you said you would remove a node. And when you said that, did you mean a node correspond to a spider? You're removing a spider and all its relevant connectivities?
Yes, I thought I don't know, but I'm only speculating. I'm not really. I guess the computation can be done. So
Matthew, I think you have your hand up also?
Yes, hello. This is a very obvious question, or rather a question with a very obvious answer. But what exactly are the challenges to writing an automated rewriting routine?
Yeah, that's a good question. I mean, yeah, I haven't really looked into automated synthesis with the ZX calculus all that much. I think, I guess, in the approach that we are taking, it's this question of like, where do your qubits flow through the circuit? Is this actually a valid circuit? Because a lot of these like flow properties that we usually have then like do some additional rewriting once you found the flow, right? And these rewrites tend to not be fault equivalent. And it is also this, we have this additional constraint of we have to have these components that are fault equivalent locally fault equivalent, and really rewriting something into the shape where then everything is exactly of this form can be quite difficult.
So even if you're not focused on a routine that's necessarily optimal, it's still tricky to find a routine that works, is it?
So, okay. I think if you don't have any purple edges, and this was a question that Sarah asked during the talk at some point also, like if you don't have any purple edges, I think the procedure that we gave in our previous paper is already kind of one way of non-efficiently synthesizing a fault equivalent circuit. The moment you get purple edges, life gets tricky somehow. And yeah, we don't really know. Like there are some examples in this talk of removing purple edges. You can read, for example, this repeating of the measurements that Shaw proposes. Previously, all internal edges are purple. Here, if you think of this as a fault equivalent ZX diagram, here we have the ZX diagram where all internal edges are purple. And here we have an equivalent fault equivalent ZX diagram where no internal edges are purple anymore, because the fault measurements don't require any purple edges. So this is a way of removing purple edges. Flags are another way, which normally only work up to some distance. So that's kind of what Goto does. With flag measurements, you can also remove purple edges, but only oftentimes people would force it and do it up to some distance. Yeah, it's purple edges are weird, and I wouldn't have an idea of how to constructively get rid of all of them, even if you gave me unlimited resources.
Okay, well, thank you.
Yeah.
I have a question about earlier you mentioned the fault-tolerant component versus the fault gadgets. Are they the same thing or they're different notions?
No, sorry, by fault-tolerant component, I meant these examples that I gave earlier. Let's see. That's a disadvantage of having so many individual slides. So these kind of things that are very naturally fault equivalent. Like, so this thing is just fault equivalent to this particular circuit under circuit level noise, right? If I just had a C0 somewhere, that would not be fault equivalent to a C0 under circuit level noise. Like a C0 in a ZX diagram under Edgewood noise is not fault equivalent to a C0 as a quantum circuit under circuit level noise. So finding these smaller components that are kind of already fault equivalent to a quantum circuit, yeah, that can be kind of tricky at times.
And where has the fault gadgets been used in the synthesis process?
Yeah, so no, in the synthesis, so the fault gadgets are more a way of kind of diagrammatically tracking entangled faults. In this synthesis process, we've been trying to avoid them because they can be difficult to deal with by hand. But like in more like for certain settings, they're really useful to kind of, for example, figure out if your circuit has hook errors and stuff. You can kind of do non-fault equivalent rewrites and just add these fault gadgets to track entangled faults. But also these can be useful for more automated ways of thinking about fault equivalencies. And these can actually be manipulated very nicely. And that's actually quite cool about them. Yeah.
Right. So I think someone just shared the reference. So
yes. I think there's two papers here that I've been, yeah. So the first one, the blocklet concatenation. Yeah, I've seen that. That looks really interesting. I think that it very much goes in a direction that I would also be interested in. Is like where if we now have these individual components, how do you kind of go to composing components? How do you do fault-tolerant composition of fault-tolerant components? I haven't had the chance to actually look at it in detail yet because we were just finishing the paper, but I think that is a really cool reference. And then Linear is sending. Oh yeah.
Yeah, I figured that for W fault tolerance, this flagging scheme where you add more and more flags might be one way. You probably would end up with a horrifying number of flags, but it might be something point.
Nice. So do they prove that this is always possible?
Yes, so they have any distance decode. You put what did they say? Just D+1 flags, I think, for the signal extraction. So something that would be a way to use that, as I said, for W fault tolerance.
Nice. Yeah, that alone would be a really nice reference to have, because if you know that at least you can always construct these, that would already kind of be a neat theoretical reference every now and then, even if it's not the most efficient.
Yeah, I'd have to read it. This was a long time since I wrote it, but I remember it being quite nice.
Nice. Thanks. Yeah, I'll look at these. I'll try to copy them somewhere.
Well, actually, I will share the all the references shared in the chat, and then I'll put it underneath the talk so everyone can have access to it.
Oh, great. Awesome. Thanks a lot. Yeah.
Problem. So maybe let's have one last call for question. I also have a question, but I want to like let other people ask. So if you guys have any last minute questions, feel free to ask.
Maybe a last minute comment. You were saying this is question of detecting regions and high weight faults. I think to me the way to think about detectors is to think about the tiling of your circuit. Both in the sense that you should, of course, obviously cover it, but you also don't want them to intersect too much, right? So you should have at least some basis for your detectors that is reasonably local, whatever that means.
Yeah.
So maybe there is some way of reason between, you have some basis for the detectors, you compare unions or intersections or whichever between the detectors, and that should have some reasonable properties.
Yeah. Do you think there's a notion to quantify this overlap or something, or what would be the right?
Yes, what I'm thinking, that you don't want your detectors to overlap too much. So you somehow want to think about the complement of the detectors also. I don't know. I don't have anything to speak for.
Yeah. Interesting. Yeah. No, I think it's quite interesting. Yeah.
So I have a question. So earlier you mentioned about you want to use a more tolerant notion of fault tolerant. You use like W fault tolerant, and that give you some saving on resources. But I couldn't see the differences between the W fault tolerant implementation of a circuit versus not W fault tolerant, just the fault tolerant implementation of the circuit. I don't see how they are different.
Yeah, sorry, I went a little quick there. So here in this circuit, we kind of do these, what are they, XX measurements transversely for all n output qubits over here and all n output qubits over here. And for the W fault tolerance, we only have to do it for W many. So if you kind of zoom in, there will be some wires where you don't have to do these additional measurements. So if W is 3, you only have to do 3 of these instead of having to do n of these. I think the savings here are not necessarily massive unless you go to really, really large cat states, and I'm not sure if people really go to really, really large cat states. But it's more about the point that I think you can save quite a lot of resources if you actually do W fault equivalence rather than fault equivalence in particular settings.
So suppose you need a large collection of cat states when you're running, let's say, a large algorithm. Is it possible to parallel the use of the ancillary qubit here, which is the plus state, so that you can actually minimize or like, push the number of ancillary qubits to as small as possible?
Yeah, I mean, I guess I mean, what we kind of suggest here is reusing this one auxiliary qubit between all these measurements. I mean, there's always this trade-off between number of auxiliary qubits and circuit depth. In that now this circuit will be very deep because we kind of have to do all these measurements one after the other. If you use a lot of auxiliary qubits, you can use W many, one for each measurement if you want to. That'll reduce circuit depth significantly, but so there's this trade-off, and I guess something similar would come to play if you prepare multiple at once and reuse the auxiliary qubits between them. It's this trade-off between depth/time and width, I guess.
Yeah, I think it would be very interesting if this procedure is benchmarked with some algorithm, and then we can see what actually happens in terms of the space-time overhead, and then we can compare with the state of the art. So I have another question about your open question at the end. So you're talking about at this point we are assuming all the the worst case errors, and we assume this uniformly distributed errors. And in the concrete situation like the IBM hardware, all of their quantum registers have different error rates. So this means that every wire have different probabilities of going wrong. I wonder if you consider that when you're doing this kind of synthesis.
Yeah, I think that would be really interesting. We don't yet. I think this would be interesting in a multitude of potential settings that you might think about is thinking about Yeah, I think there's a range of questions. If you go from adversarial noise to stochastic noise, I think there's a range of questions that open up that you can suddenly at least ask in the first place that you can't at the moment in this current version of the framework. And that would be, for example, one of them. Yeah, I think there is slightly more questions that kind of go in that direction of like, how do we even ask them? At the moment, how do we even ask them in this formalism? I'm not sure if many other people, I mean, people are thinking about these, right? And well, can we find a formal language? Maybe there is one already that I'm not fully aware of, but can we kind of possibly combine this with existing ideas on that? I think it would be really interesting.